So our goal today is to return to integrals and see how the chain theorem can be used to help us solve some difficult looking integrals. Now we only have one big idea today, is how to take the antiderivative of composite functions, but it is quite a big idea, so it will take some time. Let's start by recalling the chain theorem. So the chain theorem said that we can take the derivative of somewhat complicated looking compositions of functions here by taking the derivative of the outside function, leave the inside alone, multiply by the derivative of the outside function. And as always, every rule for derivatives gives rules for integrals since they're almost inverses of each other. Therefore, if you see a function that looks like this strange composition, this mess over here, well, it's pretty easy to integrate. So of course, if you're faced with an integral problem and you have over here an integral to look at, what you're going to recognize is, of course, that here we have an x squared and the derivative, which is 2x. And on outside, we have the derivative of a function. So of course, this cosine really is just sine, and the x squared was our inside function. So of course, the antiderivative of cosine of x squared times 2x is just sine of x squared, since by the chain rule we can compute the derivative of sine of x squared and get cosine of x squared times 2x. This is somewhat ridiculous, okay? So while it's easy to see it when you're presented with the answer, it's very, very hard to recognize, go from this integral to automatically compute on the other side. So while it's important, we are going to find a better way to do it. So the big theorem and idea from this section is that you can take the antiderivatives of composite functions. If you have g, a function whose range is an interval I, and f is a function that is differentiable on that interval, and if g is of course differentiable on its domain, as long as everything's good and differentiable, and you start out with this crazy looking composite function, then what you can do is you can compute the antiderivative by reversing the chain theorem. Okay? As long as you have what looks like the derivative of something coming from the composite, you can reverse that process. What we're really going to use though is more the second form here. Our goal is to transform our function so it looks something easier. Here, in the second integral, we're taking the integral of a relatively easy thing. It's the integral of the derivative of a function with some respect to some variable. And of course, the antiderivative of the derivative is just the function by the second fundamental theorem of calculus. So let's talk a little bit more about how this actually is going to work. So the process we're going to go through is called change of variables, and it's also called u-substitution because we often use the letter u and substitute it in. So what we're going to do is we're going to start by picking our u to be our inside function, and then we'll compute the derivative of it. Because what this is going to allow us to do is it's going to allow us to take a very complicated looking integral here, and what we can do is we can replace the g of x function with u, the derivative of g with du dx, because what's going to happen in this process then is because this integral is going to be the equivalent to a very simple integral. In some sense, you can think of the dx as kind of cancel off. And now we're left to take the antiderivative of the derivative of a function. The antiderivative here of the derivative is simply the original function plus a constant. And then finally we do a final replacement of u with g of x. Okay, so that's enough abstraction. Let's actually see an example on how it works. So while we work through this example, I'm also going to be giving guidelines for change of variables. It's a nice pattern to sort of follow every time we have to do one of these. So what we want to do is we want to take the integral of the function we have over here on the right, the integral of 4 times x squared plus 1 cubed times 2x. Now you could certainly go ahead and just multiply this all out and use your nice polynomial rules, but instead we're going to use this to practice substitution. Generally, when you're choosing what to substitute, you want to choose something that's the inside of a composite. It's going to be a term that's in parentheses, but sometimes you just have to try something and hope for the best. So in this case, what we're going to do is we're going to follow the inside of the composite part. If we look closely at our function, what we've got is inside the parentheses here, inside of this something cubed, we've got an x squared plus 1. So that tells me that I should probably choose u to be the function x squared plus 1. The next step in my process is to compute the differential of my function. So compute du equals g prime of x dx, and solve for dx. So if I take my differentials, du is going to be equal to 2x times dx, since 2x is the derivative of x squared plus 1. And at this step I also want to solve for dx. So this tells me, doing a little bit of algebra, that dx is equal to du divided by 2x. Next I want to rewrite my integral in terms of u using substitution. So basically my goal is to replace all of my x's. So I started out with the integral of 4 times x squared plus 1 cubed times 2x dx. And what I can do is I can start replacing things. The 4 is going to stay, but the x squared plus 1, using the fact that u is x squared plus 1, I can replace with a u. And I have to keep my exponent there cubed. The 2x for now will stay around, but I'm going to also now replace my dx with a du over 2x. And the reason I wanted to do that is because now I have the integral of 4 u cubed, and the 2x's we can see will cancel. Du. So it's always a matter of just replacing everything so that where we have no x's, we're all in terms of our new letters. Next I want to actually try and find my integral if I can. Well, this is a relatively easy one using the power rule. This is going to be u to the 4th plus a constant, because the derivative of u to the 4th is 4u cubed. And finally, I replace all occurrences of u with my g of x function. So this means I replace my u with my original g of x function, x squared plus 1, and just complete the rest of my integral. And if you wanted to, what you could check that if you take the derivative of this expression down here, you'll end up right here with what you started with, which is what you should have, just by the chain rule. So this is going to be the same process we follow for all of our other steps. So we're going to try another one here, but I'm not going to write exactly the steps we're going to follow, but I will write the numbers alongside the work. So here I want to take the integral of 2x minus 1 squared dx. Again, we could just multiply this all out, but we're going to practice using the chain rule. So step 1 says I need to pick something that's kind of the inside of a composite function. So in this case, what I'm going to choose is u is equal to 2x minus 1. Step 2 in the process, we want to take the derivatives. So in this case, I get du is equal to 2 times dx. And if I solve this for dx, I end up with dx is equal to du over 2. Step 3 is my rewriting step. So I start with my original integral, and my goal is now to replace as much as I can. So in this integral, what I'm able to do is I'm able to replace what's inside the parentheses with u, keeping the squared, and the dx I can replace with du over 2, so that now it simplifies down to simply 1/2 u squared du. And what I can do here is I can take the 1/2 out of my integral because of my constant multiples property of integrals. Step 4, I'm going to attempt to compute this integral. Well, I remember my power rule says that this needs to be u cubed over 3. I add 1 to my exponent and divide by the new exponent, plus c. And finally, step 5 says replace everything back in terms of my original x. So I can replace u with 2x minus 1. So I'm able to compute these integrals relatively quickly and easily, and it's going to save a lot of work, especially when we get to more difficult things. So here we have another integral. It looks pretty similar to our last one, but there's going to be an interesting thing to happen here. So what I want you to do in this video is always try to pause the video and think about the next step ahead of time. So our first step says we need to pick something for u, and hopefully you still stuck with inside the parentheses 2x minus 1. Step 2 says we need to take the derivative. So in this case, du is going to be 2 dx again. So far, pretty much the same as last time. And now we need to rewrite our integral. So I'll just copy the original one down here first, and then we'll try to rewrite stuff. And for the most part, it's okay. You know, inside the parentheses just gets replaced with u. We're going to replace our dx with du over 2. Again, in this previous step, I should have switched that, so I have du over 2 is equal to dx. Now, the problem here, of course, is we still have this x term out front here. So we need to figure out a way to replace that x. And usually what this is going to involve is looking back at our first step. So if we think, what we can actually do is we can actually use this step and solve for x. So u equals 2x minus 1 tells me that I can also write this as u plus 1 over 2 equals x. So now I can use this substitution step. So now my integral also is going to equal the integral, and I can replace this x with u plus 1 all over 2. And everything else just comes on down. And let's simplify this a little bit. So after doing some algebra, this simplifies down quite a bit into a very, very doable integral. So if we try to compute this integral, we're going to get 1/4, and using the power rules here, well, the antiderivative of u cubed is u to the 4th over 4, plus u cubed over 3, plus our constant, and finally, step 5 allows us to replace everything back with our original u. So we're going to get 1/4 times the quantity 2x minus 1 to the 4th all over 4 plus 2x minus 1 cubed all over 3 plus this constant. And so this is probably not something you would quickly look at and see what the antiderivative needs to look at. It would probably take a little bit of work. Even multiplying this thing out would take a little bit of work, but it's not so bad overall. The key feature in this example is right here, is we had to do an extra substitution step. So you're going to see this quite often when you go to compute integrals. So for the integral of sine of t times cosine of t, I really do want you to try to figure out a u to choose on your own. So the first time you're faced with this problem, what you might say is, well, let's just let u equal t. It's inside parentheses, it follows the idea there, it's something inside, so let's just go for it. So now we take the derivatives, du is equal to dt, so that was step 2. And then in step 3, we rewrite, so we get the integral of sine of t times cosine of t dt is equal to, well, the integral of sine of u cosine of u du. And nothing happened, okay? We just changed letters. We didn't actually make it look different so that it's more computable, we just changed letters. So the best thing in the world you can do as a mathematician is you can start over. So you just cross it out and try something else. So in this case, well, if you're going to try something else besides t, you have to pick a function, sine of t or cosine of t. Think in your mind which one you think is better. Either one's going to work. Let's let u equal sine of t and see what happens. So in this case then, the derivative of sine is cosine of t dt. And what's neat here actually is I don't actually want to solve for dt in this case. Cosine of t dt appears in my integral. So this means I can make my substitution step really pretty easy. So this means that the integral of sine of t cosine of t dt can be replaced by substituting and replacing sine with u and replacing cosine t dt with du. Well, that's a pretty easy integral to take. What's the antiderivative of u du? The antiderivative is simply going to be u squared over 2 plus c. And finally, I can make my final substitution step, replace my u with sine, so I get sine of t whole thing squared, all over 2 plus c. And so what you can see here is that this is a good example of one where it wasn't really clearly a composite function of sorts. The composite function, because it was squared over 2, was kind of hidden, so it was hard to see. But using substitution, we can transform this integral into something that's much easier to compute. And here is our last example of the day. I really do encourage you to pause the video, try this one, see what happens to see if you get the right answer. Okay, so let's start. So the first thing we need to do is we need to pick a substitution. What am I going to let u equal? Now, I could be very tempted to say, let's let u equal 3w, and let's see what happens there. Well, if u equals 3w, then du is going to equal 3dw, so this means that dw is equal to du all over 3. So now what I can do is I can rewrite, and I'm going to have the integral of sine of u squared times cosine of u du over 3. So here I've just simply used my replacement. I've replaced everywhere where I saw 3w with u, and I replaced dw. The problem is this doesn't quite look like something I can compute yet. So maybe I should try to compute and substitute something else, or maybe I should just start over. In this case, what I'm going to do actually is I'm going to keep going here. I'm going to choose a new letter now to substitute in here. And in this case, what I want to do is I want to stare at this thing very carefully and notice that there's sort of parentheses there. Since this is sine of u squared, there's hidden parentheses. So what I'm going to do is I'm going to now let z equal sine of u. Take my derivatives. dz is equal to now the derivative of sine is cosine of u du. And what's nice, hopefully you see this, cosine of u du, well, I got a cosine of u du there. So now I can substitute and rewrite my integral here. This integral is now going to be equal to the integral. I got to keep the squared part there, but I can replace the whole sine of u with z times, and now I can replace the cosine of u du with dz, but I still need to keep that over 3 part. So cleaning up this integral a little bit, bringing the 1 over 3 out, I now have 1 over 3 times the integral of z squared dz. And now I can start taking the antiderivatives. This is just a simple power rule. So this becomes 1/3 z cubed over 3 plus c. But I'm not done. I need to replace my z's with sine of u's. So this becomes 1/9 sine of u quantity cubed plus c. But I'm not done. My original variable was w, so I got to do one more step back. And I can replace this with 1/9 sine of 3w cubed plus c. So here's the key, is I want to get back into w form all the way at the end. So while I did several substitutions, I did 2 substitutions here, I eventually got to a better place. Each substitution made the integral a little bit easier to solve. So you have a worksheet now that you got the other day in class. You should work on the problems on the front side of that sheet, the indefinite integrals, and those are what we'll start class with. As always, try the quiz online and submit a question to Blackboard. We're going to spend all day working on this because it does take a lot of practice.